Are you ready?
Go for it.
Good morning, class. This is group P107. We work on battery management system. I have Babu, Paris, myself, Abu, and Paula working in our group. Babu worked on the simulation, circuit design, PCB layout. Paris worked on the software part, the lab view, and the my view. I myself worked on design, part specification, simulation, and circuit layout. All global. Mohammed worked on the thermistor circuit, and Paula worked on the entire distortion part. So, what is battery management system? It's like a battery health monitor. It checks three parameters like current, voltage, and temperature, and ensure they are on the limit. A BMS is a simple device which look over the voltage limitations, then make all the voltages in each cell same by using the balancing methods. So it is a protection system for overcurrent, over or undercurrent, over and under voltage, over and under temperature. So background, there are many BMS available in the market. TI, Linear Technology, they have BMS available in the market with the microcontrollers, and they have the same functions, like they do voltage measurement, monitoring, and the balancing, current measurement, and the current sensing. So in case of battery management, we have two kinds of balancing system. One is active, another one is passive. In active balancing, on the merged charge cell, whatever voltage is there, we supply to other cells and make it balance. And in passive balancing, we simply discharge this cell which has higher voltage and make it to the minimum level after doing the comparison from the software. So project overview. Our device works as a voltage and temperature measurement for each cell, and the current is measured once because the cells are in series. We have resistive MOSFET network across each terminal that will be used for discharging. And our system checks the voltage and temperature limitations and monitors the current and then make the system turn off and on, looking at the limitations. We balance the circuit by discharging, which is a passive topology. So we have specific requirement, and these requirements make our BMS very unique because we're not using any microcontroller. We're using NI-MyRadio, which is our controlling, sensing, and balancing body. And the another specific or unique feature about our device is that we're trying to discharge it up to 1 ampere because other BMS discharge in millivolts. Using milliampere currents, now we're trying to do it up to 1 ampere. And we do individual cell voltage measurements, and we log the data at the speed of 10 Hz per cell. Our BMS is in modular design so that we can add up more cells. So on our system block diagram, you can see we have power supply to relay, Hall effect current fixer, thermistor, differential amplifier, MOX, and MyRadio. We have a host PC. So how does this system work? So we see that we have differential amplifier circuit, which has the gain of 1, and it simply separates the cells connected in series and get the individual voltage measurement. We have thermistor circuit, which has the thermistor that can output the temperature in terms of voltage, and we can monitor it to MyRadio. And we have resistive MOSFET network for discharging, which is controlled by MyRadio, and we have LabVIEW programming that helps run MyRadio, and we have the host PC for the digital data log. So after this, I'm passing it to Babu for simulations.
So once we're done with the design, we move further for the simulation. There are listed the two things for the simulation. One, first thing we have to measure the each cell voltage. Second, we have to discharge the cell when the voltage goes over 3.8 volt, the more or less average voltage.
Guys, really quick, aspect. Go back. This is just a word for all of you going out. It has amazed me ever since I've been at UTA. I just sat through presentations in the earlier class. Aspect ratio on figures. I get almost every group, every semester does something with aspect ratios. What's your aspect ratio? And it's obviously stretched and not to scale. So watch aspect ratio, okay? I'm not mad, I'm just saying for future things, it makes you guys look bad. You need, besides your aspect, it doesn't have to take up the whole thing. What's your aspect ratio? You right-click the figure, go to size, lock aspect ratio, where when you stretch it, it's not stretching like that. Okay, just so you know for future, you gotta do that.
So for the voltage measurement of each cell, we come up with a differential amplifier where we put all the resistor values the same, so that it will give our gain equal to 1. For these things that we do the simulation on SPICE, we have a 2 cell of 4 volt and 2 volt. Once we put all the resistors of the same value, our gain will be 1, and the PR will be given by the potential difference between the two nodes. So here 6 minus 2 it will be given the 2 volt. This is what we did the simulation on the SPICE for the 4 cell. And once we build the circuit on a breadboard, we tested, we used this power supply as an individual cell. And once we set up one of the cell 3.12 volt, we was able to measure the actual voltage of the cell. Paula will talk more about this charging circuit.
So in this discharging process, each cell is connected to a bypass resistor and a MOSFET controlled by MyRio. The problem is the maximum output voltage that MyRio can provide is 3.6 volts. And here you can see that the source is already at 3.6 volts. So it's obvious that MyRio cannot drive this discharging MOSFET. A solution for that is to implement a high side driver that will increase the voltage in the gate by adding an extra voltage source. Also, we need to. It's necessary to add another small signal MOSFET so MyRio can actually control the discharging circuit. Here you can see two different implementations, one using an NMOSFET and another one using a PMOS. The PMOS is visibly easier to implement, and it will be used for 7 out of 8 cells. The first cell, however, cannot be implemented this way because the voltage where you can see the 7.2 volt there at the source would be 3.6, and of course it will not be enough for you to drive it. So, and here's a simulation showing the first 3 cells where the voltage source representing the voltage coming from MyRio is set to a pulse wave from 0 to 3.6, and the voltage through the resistor is also measured using a transient analysis. The purpose of the simulation is to prove that the voltage required to drive the discharge loop is lower than the MyRio maximum output voltage, and also to show that the switching time will not be a problem in our project. Here I have a total of 100 milliseconds, which is the period which MyRio will report voltages and temperatures to the user. This circuit was implemented on the breadboard and tested using voltage sources and an ammeter. There's a simple diagram, but it's a simplified diagram showing the necessary driver voltage coming from MyRio. This cell, the voltage cell that was set to be 3.5, and the measured current showing that the MOSFET was turning on and off. So the result was that a voltage of less than 2.5 was enough to turn on the small signal MOSFET, turning on the discharging MOSFET and generating a 709 milliamp amps. By comparing this, the measured current to the theoretical value for the current, it's obvious that it's a little lower, and the causes for that could be the wiring and the equipment used to implement it. Next, Abu will talk about the temperature measurement.
So I'm talking about temperature measurements. So why do we need the temperature measurements? There are 3 different temperatures that can affect the performance of the battery itself. If the temperature go really low, it will reduce the transformation of the active chemicals in the cell, which will reduce the current and capacity of the cell. And then when we get to a higher temperature, that will produce higher current will produce higher power dissipation and can lead to a thermal runaway. So higher temperature can lead to a thermal runaway, which is uncontrolled increase in temperature that can cause fire or explosion. So the temperature sensor used for this project is called NCP9700 for microchip. It's a linear active thermistor. So it's just output a voltage that is proportional to the temperature that's need to be measured. And the temperature range of this device is from -40 to 125 degrees Celsius. And the accuracy is plus or minus over the range of 0 to 70 degrees. For our project, our range is 0 to 60, so that will be perfect fit for the project. And the temperature coefficient of the device is 10 millivolt per degree Celsius, and it's only requires 6 microamp operating current. So this is just a test for the device to make sure it's outputting the voltage that corresponds to the temperature. The first one is just a room temperature, the second one is just using a finger. The second one is using a heated screwdriver. And for the accuracy of the sensor, we had to use an accurate thermometer that was provided by Dr. Ritz, and then measure the sensor voltage at the same time with the thermometer, and convert the voltage to temperature, or the sensor voltage temperature, and then the error was within the range that's specified by the data sheet. We measured with 3 different temperatures, at room temperature, at 40 Celsius and 60. So it's the error about the same, it's plus or minus 2. So the error calculated and feed it back to the software for the temperature. This is just a picture about my real interfacing with those are the thermistors here through the multiplexer, and then display the voltage. Actually, this is the voltage output of the sensor, and then there was another column with display the temperature. This is just a plot diagram showing this is 8 battery cells connecting to 8 thermistors, and then the 8 thermistors connecting to a multiplexer, and then the multiplexer output connecting to the Mario analog input, and then the Mario will control the display, which cell temperature will be displayed and displayed on the host PC. And this is just a multi-sim circuit. It's a dummy circuit. There's no way to simulate this. But it's just showing the same thing. You have 8 temperature. The error indicates the error is battery cells, and this is the sensors, and then going to the multiplexer to my reel. Now I'm gonna let Babu continue.
So after testing and verifying all our simulated problem, cell voltage measurement, temperature measurement, and discharging circuit, we move to the next level of designing the circuit on PCB board. This is just the schematic on PCB. So we use the light version of Eagle PCB 6.5. It comes with a dimension of 4 inch to 3.2 inch X and Y axis. And the total component we use on excavator is 66 resistor, 8 power resistor, 8 differential amplifier, 8 capacitors,